Machine Chillers Incorporated has developed a new cooling system based on a vortex tube, which uses, unlike conventional chillers, uses air as a working fluid. Our task here is to characterize the chiller's performance relating the input pressure to the cold and hot output temperature and cold and hot mass flow rate. There are 5 measurement locations in which we'll measure either temperature and pressure or mass flow rate. The main components that we are using with the system setup are the vortex tube, the accumulator, heat exchanger, air supply, whether that's a motor, compressor, or building line air. And finally, the thermal load, which in this case is the aluminum block. Using the data collected, we will determine the experimental thermal resistance and from the experimental thermal conductivity of the aluminum mass load.
Now going into the procedures of the lab, the diagram shows the setup and the process of the experiment. It begins by pumping in pressurized air into the system. Please note, for this week's experiment, the air came directly from the building air line, but for next week's experiment, there's also going to be a motorized air compressor in order to find the transient response. But this experiment was only to find the steady state response of the system. From there, the air travels through the pressure regulator, followed by the first temperature reading, where we expect the temperature to be higher than the ambient temperature. The air will then run into a heat exchanger, where it will drop the temperature back to ambient. The air will then run through the accumulator tank, which holds any excess air that goes beyond the set pressure, in which case the pressure and the temperature will be taken before it flows into the vortex tube. Once in the vortex tube, the air will then be separated into a hot flow and cold flow. The hot flow will come out one end, where the temperature and mass flow rate will be recorded. The cold flow will come out the other end, where the respective temperature and pressure will be recorded. The cold air will then continue into the insulated load. After the temperature is recorded for the load, another temperature and pressure reading will take place, followed by the mass flow reading. The ambient temperature sensor isn't actually a part of the flow of the system. So in order to take that measurement, the thermocouple must be switched out once we reach steady state. As the vortex tube is the most important component of this experiment, it is vital to explain how it separates the hot and the cold flow from the input air. Once the air flows into the tube, it will be spun at a high speed. Since hot air is lighter, it will stick to the outer edge of the chamber, where it will then flow through the control valve and pushed out into the hot exit. Cold air will be maintained in the middle of the chamber and will continue to flow out into the cold exit.
When we started analyzing our Lab 1 data, we immediately realized that something was wrong with our experimental setup. When comparing our data with the rest of the class, visualized here by data given to us by our TA, our steady-state cold output temperature is between 5 and 10 degrees Fahrenheit hotter than it should have been. We later learned that this was because our vortex tube was not correctly set up and had dirt in it. We decided that it would be interesting to compare the results generated from our faulty data with those generated from the TA's data. So for the rest of the section, I will be presenting results from both datasets. As a side note, this data also showed that our steady-state regions were not actually very steady, varying by as much as 3 degrees. This suggests that some of the steady-state assumptions we made for our model may not be valid. The obvious difference between our data and the TA's data was that the TA's steady-state cold output temperatures were much colder than ours. When plotting these temperatures against input pressure, this resulted in a slope roughly twice as large as for our data. Importantly, however, both datasets showed similar nonlinear behavior, characterized by starting and ending above the regression line, with all other points below the regression line. This suggests that the nonlinear behavior found in our data is representative of the behavior of the system, despite our faulty vortex tube. In terms of plotting the hot output temperature against input pressure, both datasets showed similar linear behavior, with roughly equivalent slopes and intercepts on their regression equations. The TA's data was a slightly better fit for the linear trend line, but in this case our data appeared to represent the true behavior of the system. The results for the cold mass flow rate plotted against input pressure were also remarkably similar. Our data did yield a slope about 30% larger than that for the TA's data, primarily due to our larger range of values, but both datasets showed very close agreement with the linear trend line. Finally, we plotted both datasets' hot mass flow rates versus input pressure. There are two key things to note with these graphs. First, the TA's data had a slope almost 3 times as large as our data. This is a result of the much higher cooling rate that occurred when a correctly calibrated vortex tube was used. Second, the TA's data was significantly more nonlinear than our data, primarily due to their nominal 20 psi data point. This suggests that the true behavior of this plot is nonlinear, rather than linear as our data would suggest. The last step in the analysis for this lab was to calculate the thermal resistance of the insulation block. One key assumption for this calculation was that T3 was roughly equal to T ambient. These plots suggest that this assumption holds true for both our data and the TA's data. The thermal resistance values calculated from our data, the TA's data, and theory are tabulated here. The key takeaway from this data is that even using the data given to us by the TA, we could not match the thermal resistance predicted by heat transfer theory. This makes sense, as the theory assumes several ideal cases such as constant pressure and no heat losses. This suggests that our theory does not match the behavior of the experimental setup in reality. Another interesting pattern in this data is that, with the exception of the 80 psi case in our data, thermal resistance values seem to increase with pressure. This could be due to improved thermal efficiency at higher pressures, which might be something worth incorporating into a revised refrigeration.
Further experimentation utilizes a motor-driven compressor in conjunction with the vortex tube, and the relationship between motor speed and input pressure is determined at 0, 20, and 40 psi. After determining the offsets from the steady-state data collected at 0 psi, the heat exchanger and accumulator tank are examined to determine if they are necessary. The transient cooling of the load is then modeled while being cooled by building air and then again by the compressor. When the load is being cooled by building air, the pressure should be at 80 psi. When the load is cooled by the compressor, the pressure should be at 40 psi. Since these are separate tests, the load should start at around ambient temperature for each test. Finally, it is important to calculate the uncertainties associated with each value. Discrepancies between the model and experiment will be either from sensor uncertainty or model errors. The following links and references were used while proceeding through data collection and analysis. Thank you for listening.